So this is the Phi GUI, as you will see it when you have successfully installed Phi and brought up the data set that we provided for the course. So this is this mini data set. Let me try, I'm just gonna make it smaller like this to hopefully make the displays a little bigger for you. Hopefully that helps. So there's a bunch of different windows here. And actually one thing that helps with Phi is if you have a big monitor, so you can get a nice amount of detail on all the windows. So I'm just gonna walk through these different windows and what you're seeing and what they're for. And then we'll talk about sort of going through spike sorting. And by the way, let me just say that you can rearrange the layout of the windows however you like by sort of dragging things around like this. You can sort of like hide things behind other things and then they become little tabs. So however you want to do it, you can set it up. So just FYI on that. Okay, and now I messed it up dramatically. Okay, so here we go, we're back. Okay, so the first view that's sort of your main point of navigation within the GUI is the cluster view. So cluster view upper left, and this just lists all of the clusters, all of the units, putative neurons that Kilosort has found, and gives some basic information about them, what channel the peak waveform was on, what shank it's on if you have multiple shanks, the depth along the probe that it was found, the firing rate, some measure of amplitude, although these are not in units of microvolts, and the number of spikes in that cluster. And the number of spikes for all of these neurons are small because this mini data set only has a small snippet of time. And you can pick different neurons by just clicking in this cluster view. And let me flip back over to the waveform view. When you're picking different neurons, we're seeing not only the waveform of those neurons, but also some of these other views are updating to show you different things about the neurons. And the other thing you can do in cluster view is pick multiple neurons. You can shift click to select all within a group, and you can see the waveforms of all of those different neurons plus all of these different plots, or you can control click just like you normally would do to select things, and then you can get different neurons that way.
Nick, there's a question about what data set you're looking at now. Is it the one?
This is the mini data set. It's the one we provided for the course. Yep. So you should be able to find neuron ID number 1 that looks like this, I hope. Yep. Okay. So similarity view, the next one down, looks the same as cluster view. It's got a list of all the clusters in the data set. It also has one more column, which is similarity. And what that's indicating is the similarity estimated by Kilosort of this neuron. In this case, the first one here is number 195, the similarity between that neuron, 195, and the neuron you have selected up here in cluster view. So it's judged that number 195 is similar to number 1. If you click it, then you can see both of them side by side, and we can see that in fact, they have similar-ish waveforms and are on similar channels of the data set. But we'll come back to this similarity view in a moment after we look through the other views. Okay, so Correlogram View is giving you the auto-correlogram in color of any of the units you have selected. So the blue autocorrelogram, the red autocorrelogram, and the cross-correlogram in white, which is basically the probability of finding a spike of the blue neuron relative to times of the red neuron. And the thing that you can do to sort of investigate things in more detail in this view is to change the time window and the bin size. So if, for instance, I want to zoom in on the refractory period here to see in detail how this refractory period looks, I can click this little menu button. Hopefully you can see the menu popped up, and there's set bin and set window. So if I set window, say to rather than 100 milliseconds, let's say I set it to 20 milliseconds. So now you can see I've zoomed in on the x-axis, and now we're only seeing 20 milliseconds of data. If I set bin to say, rather than 1 millisecond, say 0.1 milliseconds, then I'm zooming in on the time resolution, and now I've still got this minus 10 to 10 milliseconds, but I've zoomed way in. And so actually now we've been able to see these gray vertical lines are a 2 millisecond plus or minus 2 millisecond indicator. And we've been able to see by zooming in that actually all of the spikes are outside of that 2 millisecond window, indicating a clean refractory period, as I'll talk about more in a minute. Now, quick thing about how to navigate this GUI efficiently. You can do all of the things with menus, but hopefully one thing you can see as I'm hovering over this set bin or set window text is that down here at the bottom, so watch the bottom bar here as I hover over, You can see some help text, which says what this command is going to do. And you can also see this thing that says alias, in this case, CB, alias CW. So this is just a way to make navigating the GUI a lot faster for sort of expert users as you get better at it. The way you use those alias commands is by typing a colon. And if I type a colon, then I get a little prompt down here in the lower left. So in the bottom left, you probably can barely see it, but it says colon and then a little cursor. And now I can type a command. So CB is the alias for a Correlogram bin size. And I can type a value 1, and my Correlogram bin size went back to a bin size of 1. And so again, you're just figuring out what those commands are by these aliases to hover over. So I can do the other one is CW. So I can do colon CW, and then say 200 milliseconds, and I zoom way out on the Correlogram view. Okay, so there's a whole bunch of different aliases, and once you get fast at things and you're finding yourself clicking through the same menu option over and over again, you can look for the alias and you might be able to speed up your workflow. All right, next view is the Amplitude View. So this view is showing, as a function of time on the x-axis, showing the amplitude of each spike. And this is the amplitude parameter that Marius described, which is a scaling factor applied to the template to fit each spike. And so it's a relative amplitude. Each blue amplitude spike is the amplitude of the blue spike relative to all the other blue spikes. You cannot really compare the blue amplitudes and the red amplitudes to each other because they're on different, they're relative to each of their own templates. So don't get tripped up by that. But we can see, what we can look for is whether this amplitude is stable across time. And in particular, we can look for whether that amplitude dips down into the noise. So Marius showed an example of that, and you can review his talk to see where you see the amplitude dip down into the noise if it's unstable and sort of disappears over the course of the recording. Both of these neurons have nice Gaussian looking profiles in this marginal distributions, indicating that these neurons are above the noise floor. Okay, firing rate view just shows the firing rate of the neurons across time in the recording. This is useful if you want to see whether some neurons are only active at certain parts of the recording. Template feature view, you will normally get this if you run Kilsort. Unfortunately, mini dataset was run on an old version of Kilsort, which did not produce the template features. So I can't talk about that, but Marius did show some template feature view plots in his talk. And basically the idea is that it's looking at the most specifically well-designed features that can discriminate the blue from the red neuron. And these are all at 0 because, again, it didn't compute them for these particular neurons, but you would normally have those. So it's a particular feature space that's useful for discriminating the blue from the red neuron. And likewise, feature view is plotting some principal components of the blue and red neurons. And it's plotting it for some of the principal components as a function of time, and which principal component is indicated by these little axis labels. So 28A means channel 28, that's this one, as you can see with this label 28. Channel 28 and the first principal component is A. Channel 28, second principal component down here would be 28B. And then you have different principal components against each other to give you different views of feature space where you might see neurons discriminated. So for instance, we can see that 26B versus 26A is not super useful for discriminating these a little bit, but maybe 26B versus 28A is a very useful feature space for discriminating these neurons. So you can look around that view. This can also help you see whether the neurons are stable over time. Okay, so coming to the waveform view. So this is showing sample waveforms from the different neurons that you have selected, and it shows just a limited number of them. This is not showing you all of the waveforms of these neurons. It just shows you a selection, something like 20, 25 waveforms just overlaid. And this allows you to see whether they are all consistent or whether, in fact, you have multiple different types of waveforms within your cluster. So sometimes you'll see, some low amplitude waveforms and some other ones that are high amplitude, and that would indicate that you might have a mix up with multiple spikes in the same cluster. Okay, and then the red and blue next to each other are both the waveform samples from the same channel. This is from channel 28, and this is also from channel 28, but this is from the blue neuron, and that's from the red neuron. And they're kind of geometrically arranged according to where they actually were on the probe, according to the channel map. Okay, and you can do a couple things with this view. One is you can scale. Here I'm holding control and moving the scroll wheel up and down. If I hold Shift, nope, that one's not working for me. Not sure why. Okay, if I hold shift and do arrow keys, I can move these apart or apart that way. Control arrow keys, I can move this way. Okay, so there's a few different sort of mouse things to zoom in and out. You can also right click and zoom around. So that can give you, making sure you have the best view of the waveforms. But an important thing you can do is overlay the waveforms with each other. So this just plots them on top of each other. I just pressed O, and again, these are all in here. So toggle waveform overlap O, that's all I did. And then the last thing you can do is switch to different views. So I can press M and I get the mean waveform. And so now this is just the mean of all of those spikes. You can see that indeed it looks like the mean. And now I can overlay those, for instance, and get a nice view of whether these waveform shapes are really exactly the same or not. In this case, not. Okay, so that's waveform view. Okay, hiding behind here, I have trace view. This is plots of your actual raw data. Again, you can this is right clicking and dragging around. You can get a view of your raw data traces and where it's found spikes. And one nice thing you can do on this view, if you're looking through here and you see some neuron that you want to investigate more, like maybe this neuron, you can actually, I think it's control and then click, and now it's selected that one neuron. And so if I switch back to waveform view, this is the neuron that I've now selected from the trace view, and you can see it turned blue. So I can select that one instead. And now I've got a different neuron. So that's a pretty useful feature if you're kind of investigating trace view and trying to figure out like what's the deal with certain features that you see. And yeah, and it should, and this is also useful like the Kilosort GUI for highlighting where it does and does not find spikes. So for instance, this run of Kilosort maybe didn't work super well. It didn't find any spikes there where it looks like there's a spike. And likewise, maybe there and there. But most of the places that there are spikes, it has found them. Okay, so that's trace view. Back to waveform view. Okay, we talked about feature view. ISI view, this is just the inner spike interval histogram. It's very related to the autocorrelogram, but it's just the inner spike intervals. So if you're used to looking at that one, you can look at that. This view here, the cluster scatter view, is the depth along the probe on the y-axis and the amplitude on the x-axis. And this, again, is a way that you can sort of pick individual neurons from your probe. So like, for instance, I think I just click on that guy, and now I've selected that neuron up there. And I can click on this guy and select a high amplitude neuron down here. These are the high amplitude neurons out to the right. If I pick one of these, it'll be a low amplitude neuron. You can see I can barely see anything at all. And then this final one, the probe view, shows the layout of the channels, and the highlighted ones are the ones that you're seeing here in the waveform view. So if I click a neuron up here, it exists on these channels. So I still see a grid of a few channels, but now these are from different channels up here than the last neuron that we were looking at. Okay. Let me pause and take questions about just the mechanics of using this GUI, or any plot features that you've seen, or any questions about just literally how to navigate this GUI. And then we're going to talk about what you should look for and what process you should use.
I have a technical question before you get into the specifics. How bad would it be if you didn't use this GUI? If you let Kilosort do its work, and then you just run with it, which is something that if you have a ton of data, you're forced to do, because there's just no way you're going to manually curate. So what's your view?
Yeah, and I think what Marius described is what I agree with, which I think what he said is what you want to do is definitely for your first data sets, which are going to have your particular brain region, your particular species, your particular noise levels, and other recording configuration details. For your first recordings, you definitely want to pull them up in Phi and investigate carefully and make sure you think things are working, and see how things look. If everything looks beautiful and fine, then you can maybe immediately feel confident to go to a mode where you're never looking at Phi again and you're just trusting the results. Maybe look at a few data sets before you feel that confident. So I think you can get to that place where you're not going into Phi, but I would definitely look at it at first when you're just starting, because this is just, yeah, it's basically a way to do the sanity checks and the quality checks. Okay. Yeah, were there any questions in the Q&A on this stuff? Let's see. Horizontal gray line in the Correlogram view. Good question. In the Correlogram view, there's a horizontal gray line here. which is the mean firing rate of the neuron across all time points. And so that's the expected level of spiking in a bin if that time point is just independent of the other time point. And so the fact that in this refractory period segment here, the spiking is much lower than the overall mean is a good sign for this neuron that it has little contamination. We'll talk more about that in just a sec. Proper criterion based on autocorrelation, we'll get to that in a sec. Let's see, what's thumbed up? Can similarity view select more than two clusters to compare together? Yes, it can. So if I select that one and this one, then yes, I can get 3 clusters, 2 of which come from similarity view. Yep. Okay, so let's talk now about what you should look for in these different views. And then we'll talk about sort of the process to go through. So the question that I'm going to start with is, and let me go up to the, so I had sorted, by the way, you can sort the cluster view by different things, like say the number of spikes. So I can pick the highest firing rate neuron here, or by the amplitude. So I can pick the highest amplitude neuron here, this guy. So let's talk about broadly, non-quantitatively first, what are the characteristics of a good neuron? And by good, I mean a neuron where you can feel confident that the spike times that you get with that cluster are all from one individual neuron, and they are all of the spike times from that one neuron. So you're not missing any spikes and you don't have any false positive spikes. So what are the characteristics that might lead you to be more confident that a neuron is a good neuron? So number one is the amplitude of the spike. A high amplitude neuron is literally further away from the noise and further away from other neurons that are around. And so a high amplitude spike like this one will be relatively better than a low amplitude one. I'm going to scroll down here and pick some guy that has low amplitude. Like this one, really low amplitude. And it's simple to imagine that this low amplitude one is evidently a neuron that's further away from the probe. And there will be more neurons that could look similar to this because you just don't have much detail in the spike waveform and it's close to the noise. Okay, so high amplitude is better. Second thing is the autocorrelogram should be clean, or the ISI view should be clean. Again, these are almost the same thing. And what this is referring to is the fact that real neurons have the property of having a refractory period. That means a real neuron cannot spike within a couple of milliseconds from the time it gave a different spike. So if it spiked at time 0.0, it will not spike a real neuron within at least about 1.5, maybe milliseconds from the time it spiked before. And so if you see, like we do in this case, that there are some interspike intervals less than 2 milliseconds. This is 20 milliseconds, so 2 milliseconds is these first 2 bins down here. Or in the Correlogram view, if you see that there's sort of fill in between these vertical bars, which are at 2 milliseconds, then you would be concerned that this neuron must have some false positive spikes because a real neuron shouldn't have been able to spike that rapidly in succession. And if we go back to our high amplitude guy here, we can see that indeed this neuron does not have any spikes occurring in that segment of the autocorrelogram. Let me pick a different one and see. Okay, yeah, so here's a different one where, and you can see the difference between this one and this one. I'll pick both of them at the same time. And let me even pop this Correlogram view out here so we can get it bigger. So the difference between, and let me, okay. So the difference between this one and this one, the red one and the blue one, so they both have a nice big gap in just around time 0, right? They don't have any spikes right around time 0. That's good in both cases. However, you can see something important, which is that this blue one has a lot of gaps at times other than 0. And presumably the neuron could well have spiked at those times. It just didn't happen to by chance because this neuron only has 154 spikes in this particular recording and it's a low spike rate. Whereas this one, the red one, having a much higher spike rate, 16 spikes per second, rather than 2.5 spikes per second, this higher spike rate has sort of filled in all the rest of this, giving us really a lot of confidence that this gap here is not by chance. So this is an important point about using the Correlogram, which is that it's only useful as far as you have enough spikes to get a confident estimate of the Correlogram. And for this blue neuron, I would just really not say that you have that many spikes. So you can help yourself here. First of all, it's going to do better for high firing rate neurons, but you can also help yourself by having longer recordings. So if it's all the same to you to record for 15 minutes or 45 minutes, record for 45 minutes, because then your confidence in your spike isolation will be that much better. I mean, just think about from a big picture logically that you will have many more examples of each spike waveform for the algorithm and for your quality metrics to assess. Okay, so that's the Correlogram view. Okay, amplitude view, the thing that we're looking for here is whether these amplitudes indicate that the neuron has run into the noise floor. And you can see that these gray spikes, which are just from other neurons that are around, have this hard cutoff on the bottom, but they don't have a hard cutoff on the top. And that's because basically you expect any biological variable you measure, like the spike amplitude, to be normally distributed, Gaussian distributed, like these blue and red curves. But if they're not normally distributed, then that can indicate that you're missing spikes to the noise floor. So this looks like a half of a Gaussian distribution. So this neuron, which has a low amplitude, is probably missing a bunch of its spikes to the noise floor. So that's a particular kind of error that this neuron will have, that it's probably missing some spikes. This does not indicate false positive spikes. That's what's indicated by the Correlogram view, which again in this neuron does indicate some. So this neuron probably has both some false positive spikes and some missing spikes due to the amplitude cutoff. Okay, and then the last thing that you really want to look at, I mentioned before that in the waveform view, you can look for clusters that need splitting by seeing the presence of multiple different kinds of waveforms. And you will see that also in the feature view if you have two clusters of blue points represented, and then you might need to split them. And splitting them is just an operation that you do in the GUI. This is described online, but you basically use some features to draw a little shape, splitting out the two sets of spikes that you want to split, and then you just press K for split, which again is in one of these menus. Split is K, and that will split the spikes into two different clusters. And by the way, you can always do Control Z to just undo anything that you did, and you can also make sure to remember to do Control S for save anytime you make changes to your sorting that you want to save. All right. Let me just check my slide real quick and make sure I have said the things I wanted to say about broad quality metrics. Okay, there's actually, so one more, and this is going to lead us into the process that you're doing when you're going through use of this GUI. Let me go back up to the top here. Let me pick this neuron, and let me pick the next most similar neuron. So when you want to start doing the manual sorting, you can pick, again, we talked about the similarity view, it has this most, the one, you can press just spacebar to activate it. That's a hotkey to make this fast and easy. And in this case, actually, we can see that, in fact, these two neurons look totally identical to each other. Look, all the spikes on every channel is exactly the same. We look at the means are perfectly overlaid. And then let me put my Correlogram view back over here so we can see it while we're doing this. Okay. And if we look at the Correlogram view, well, actually, this is not a great example. So in general, this neuron has low firing rate, so it's hard to interpret the Correlogram view. But in general, if both of the neurons that you're looking at have refractory periods themselves, and the cross Correlogram also has a refractory period, which this one maybe does, then you can have confidence that they're the same neuron. But again, that conclusion will be drawn with higher confidence with more spikes. Okay, so given the similarity of these spikes and the weak but okay evidence from cross-correlogram, we could conclude that these neurons are these spikes actually come from the same neuron. So what we need to do is put them together in the same unit. Otherwise, each of these units will be missing some of the spikes from the other unit. And so one of the characteristics of a good unit is that it should be dissimilar to any other clusters. Right now, it's very similar to this other cluster. And so we need to merge these. That's this other main operation in the clustering, G. And so you would do it just by pressing G. And now we've got a new cluster, now has a higher firing rate, which is great. We can see some sample spikes from the new merged cluster. And now we can press spacebar again to see the next most similar cluster and try to make a decision about that one, whether it's the same or not. Looks like, again, it has really the same waveforms on the same channels. And so we might merge this one again. Okay, so that's all of the sort of operations and things to look for. And now we're going to talk about the process. So let me bring up Flora's slide here. Flora made a nice flowchart. Let's find it. Okay, actually, I'm going to start with this slide. Share screen. Okay, this one. Okay, so are you seeing the screen? I don't see people anymore, so
it's black for now, but hopefully it's coming.
Okay, let me give a sec.
Yeah, it's there.
Okay, great. So this is just that list of characteristics of good neurons, and this, again, this is a non-quantitative list of what things you ought to be looking for. It ought to have a clean refractory period, indicating that it has no false positives. It ought to have large amplitude, just indicating that it's likely to be better isolated from other neurons and far from the noise level. It ought to have a dissimilar waveform to anything else nearby. The spikes ought to be consistent from spike to spike. You don't want to see multiple types of spikes within your one cluster. And you don't want spikes to be lost below a threshold. That was what we were seeing in the amplitude view, because that would indicate that you're missing some spikes from the neuron. So these are general characteristics of good neurons. And there are quality metrics to quantify exactly how much of a problem each of these things are. Now, these are just estimates, and unfortunately, I cannot tell you that there's any single one quality metric that's going to, give you a 100% answer that you can completely trust and will be perfect in all cases. All of these metrics, and by the way, this plot, I should have put the link on here. This plot, this table comes from the Allen Institute Quality Metrics repository, which I think is the best place to go for some code. It's in Python for computing quality metrics. You can see that they've got a bunch of different ones, and they've given some citations for some. This Hill et al. Paper, by the way, is, I think, a great reference for getting started on quality metrics. So each of these quality metrics gives you some information. Each of them will have certain situations in which it is not useful. For instance, there's a quantification of the estimated number of false positives based on the rate of refractory period violations. And this is great to quantify, but it will be problematic when you have a low spike rate, like I described, and you can't, and it'll look like you have no refractory period violations, when in fact you could just get that by chance. So that's a caveat on that metric, and there's caveats on all of these metrics. So you want to look at these quality metrics, but it's not the case that I can just tell you compute this, this, and this, and put these thresholds and never think about it again. Unfortunately, you'll need to think carefully about it for your particular experiment and your particular data sets. These things will also vary by brain region, for instance. Okay, so how then should you approach this process of manual spike sorting? So here's Flora's slide, and here's the process that you should go through in a flowchart format, which I think is very useful. So let's just talk through the flowchart, and then we'll put it into practice over in the GUI. So first, does the unit look like noise in the waveform view? And the C step number 1, C step number 2, Flora has accompanying text, and we'll make sure this is on the PHI documentation where you can read more about this and have this as a reference. Okay, so does it look like noise? And if, oops, I think the yes and no is maybe backwards. Okay, so does it look like noise? If it does look like noise, then you should classify it as noise. And that way it will not show up in your further analyses. If it does not look like noise, then you can go to step 2. Step 2 is about the amplitude view, looking for those missing spikes that suggest you're at the noise floor. Are there too few spikes, or are they clipped in the amplitude view? If they are, you could classify it as MUA, indicating that you're not confident that you have a well-isolated single neuron. So MUA, multi-unit activity, is what that stands for. And I think in general, people use this as a general classification to say, I'm not confident that this is a good isolated single neuron. I either don't believe that I have all the spikes from this neuron, or I don't believe that all the spikes I have are from this neuron. That is, I believe I either have some misses or false positives, in this case, misses. So that could be classified as MUA. What another way to say what we mean by MUA is you might include those spikes in an analysis where you're happy to get all spikes from all neurons that you recorded without regard to which neuron they came from. And there are many analyses, like for instance, if you're just trying to calculate receptive fields and see whether the stimulus you presented was in the receptive field of the neurons, maybe you know that the receptive fields of nearby neurons are all the same, and you can throw them all together and get a good receptive field estimate of the local population of neurons. So that would be something where you can include all of the multi-unit spikes. So we're not going to throw them out, we're not going to classify them as noise, but we're not going to analyze them for analyses where we need single neuron isolations. All right, so if that amplitude view looks good though, then you can look for seemingly different spike groups in amplitude view, waveform view, feature view. This is looking for multiple different types of waveforms or features. And then you could try to split with the drawing the shape in feature view like I showed you. Wait, this bifurcates and I'm confused now. Okay, let's go to the next one. So is there a high percentage of refractory period violations in the Correlogram view? So again, the high percentage of refractory period violations will indicate that contamination, the false positive spike, so that will land you in MUA again. But if not, then you want to look now whether there are other neurons, other units that seemingly come from the same neuron, like we saw in that one example just a moment ago, because then you'll want to try to merge those units and check again whether they have refractory period violations once you've done the merge. And if all of those things pass, so you have a good looking waveform, you don't see that you're missing spikes there, you don't see any multiple clusters, you have checked for all the merges and done any merges required, and then you still have a clean autocorrelogram, this is when you can classify a unit as good, and maybe even provisionally classify as good pursuant to some quality metrics that you might run later. Okay, let me stop the share here. And so now we're going to go back to the GUI and just quickly run through that process just once on an example neuron, because your homework assignment will be to run through it on all of the neurons. So let me share again here. All right, so let's pick this neuron. So this neuron was the one we looked at with the high firing rate, and we can see the clean refractory period. So in Flora's chart, she suggests that we start with, sorry about that. She suggests that we start with the looking at the waveform. And I would say this waveform looks pretty good. It's not as high amplitude as the other one, but it's decent and it exists on multiple different channels. And the waveforms on the largest channels are pretty consistent from spike to spike. Actually, on this channel, they're not so consistent. You have some that look like they're a bit different. So we could be a little bit concerned. The feature view looks pretty good though. I don't see evidence of two really distinct clusters, although there are definitely some spikes that are kind of off to the side here. So let's give this a pass. I would say this is good enough. We like the amplitude view here. We're not hitting a noise floor. This looks like a nice Gaussian distribution with both tails. And we have a clean refractory period. So the last thing we need to check is whether there's any neurons we need to merge. So I'm going to press space and bring up the next closest neuron. Okay, and this is now a great example. Both of these neurons have pretty similar autocorrelograms, but look at the cross-correlogram. The cross-correlogram has the same size dip in the refractory period as both of the neurons' autocorrelograms. And this is a really good indication that this neuron, these two units need to be merged with each other because for them to share a refractory period like that with millisecond precision is really unlikely to happen unless they're really the same neuron. And we can just double check that by overlaying the waveforms and indeed seeing that these neurons have super similar waveforms to each other. So we will merge. And then we would want to go through that multiple times. So this cluster has very few spikes in it. And indication from the cross-correlogram is a bit more ambiguous. There is some contamination in there. It's a bit of a dip, but some contamination. If we look at the spikes now, these are starting to get sort of even more noisy, I would say. And let's just see what the mean looks like. So yeah, so in some of these channels, the mean is like looking a little different. So in this particular situation, the thing that I would consider is that our main unit has 1,300 spikes, and this unit we're considering to merge is only 89 spikes. And so whether we merge this this unit or not, the total spikes that we're working with is going to change by less than 10%. And so maybe we will err on the side of caution here and just throw away these spikes as being multi-unit activity because of this refractory period evidence, knowing that we're not giving away a large percentage of neurons, even if we're getting that, a large percentage of spikes, even if we're getting that wrong. So let's go ahead and call that multi-unit. And the way that I can do that is, okay, so to label things, you can use these drop downs. So best refers to the blue unit, the one that you've got selected in cluster view. Similar refers to the red unit, the one that's most similar to the blue one. And in this case, I don't want to make an adjudication about the best. I want to make a judgment about the most similar one. And here I want to move similar to MUA because I'm deciding that that's sort of MUA spikes. So I move similar to MUA, it becomes kind of gray in the list here. And now it moves on to the next most similar cluster. And now we can see that this cross-correlogram is really flat between the two, really no indication that these are the same neuron based on the cross-correlogram. And so I will take only the briefest glance at the waveforms and see that indeed the waveforms are not the same. Look, they're a totally different spike width. And this indicates then that the neurons are really different neurons. And so I can skip this red neuron. We'll come back to it later with a different judgment, and I would just press spacebar to skip over it and go on later. Okay, so then I can skip through a bunch of these and see whether there's any that need merging. At some point, they start to get less and less similar to the one I'm considering. And at that point, I say, okay, I must have looked at all the very similar ones to my blue unit, and there's nothing remaining. So now it's time to make a decision about the blue unit. How does it look? We started out with the judgment that its waveform was pretty good, and it still looks pretty good. We started out with the judgment that its amplitude and refractory period was pretty good, and they're still pretty good. So I'm prepared to go ahead and call this neuron good, move best to good, Alt G you can also do, and now it's going to turn green in the list, and we'll move straight on to the next unit in the list. That's the process. Okay, so I want to give Max a couple minutes, but let me just give, sorry, Max, one more thought about this whole process, which is related to what I said about how it's hard to make any definitive statements about a certain quality metric means neurons are either good or bad. What instead you need to do, and this is really important, so I just want to emphasize this really carefully, you need to think carefully about the analysis that you're trying to do and the scientific conclusions you want to try to draw from your neurons, and think about what kinds of errors would be problematic for that analysis. Let me give an example. If you are trying to make, if you believe that some neurons in, say, primary visual cortex have 2 peaks in their orientation tuning curve, then this is an analysis that is really sensitive to not having false positive spikes. Because if you have false positive spikes, you have spikes from 2 neurons in your single cluster, and that orientation tuning curve has 2 peaks. Well, maybe it's because you had 2 different neurons, one that had a certain peak and another that had a different peak. That's an analysis that you have to be really sure to exclude false positive spikes. And so you're going to have a different quality threshold for that analysis than you would for other analyses, depending on the requirements of the analysis. And one thing that you can do, this is an idea from Kenneth, I'm just going to show one last slide. One thing that you can do to help yourself be confident that a spike sorting problem is not the reason you're getting a certain analysis result. I know you're seeing the software view, not the presentation view, is do this kind of plot where you plot the effect of interest, the analysis effect of interest. In this case, it was something like spatial information as a function of a spike sorting quality metric. And the question is, does the analysis effect of interest, in this case, spatial information, as you get higher and higher quality neurons on some quality metric, in this case, isolation distance, does that effect go to 0, or does it asymptote to something non-zero? And so in this way, you can look at all of your data and take it all into consideration, but also see whether, on the few really, really good neurons, whether that effect is actually disappearing. And that will be a really nice way to combine in a thoughtful way your quality metrics without having to draw a hard threshold, combine your quality metrics with your analysis conclusions. So I think this is a really good approach when possible, and you should keep it in mind.